Hey guys, so in this video we are going to be talking about differential equations, right? And quantum mechanics has a lot of differential equations, a lot of solving differential equations, to the point that most courses will actually require you to have taken a full course in differential equations. My goal with making this quantum mechanics course is it's not like that, right? You can learn quantum mechanics without having taken a course in differential equations. However, there are some differential equations that are very, very, very important to understanding how to solve in order, or at least understanding the solutions of, not necessarily how to solve, in order to really understand the theory. Any other time that we're solving differential equations in this course, I'll walk you through the solutions and also um, really understanding the solutions and the solution process won't be essential. These differential equations, the ones that I'm going to talk about in this video, and understanding the theory that I present in this video, which will not be very long, that's the part of differential equations that is really essential in understanding quantum mechanics. So to start, I have this basic differential equation, and if you've taken Calc 1, you'll actually know how to solve this, right? It's that the derivative of y with respect to x, where y is some function, is equal to some constant k times y. The solution of this is y is equal to some constant c, right? And it can actually be any constant, no matter what k is. The c will work if it's, 0 is trivial because then y equals 0, but that works, right? The derivative of 0 is 0. But c can be any constant, and this solution works. And we'll see later how you may be able to determine what those constants are if you're applying this equation to a specific situation. Right? But we're given this equation. We know the solution is y is equal to some constant times e, Euler's number, raised to the power of k times x. And you can plug in this derivative and see if this works, no matter what c is, and you'll see that it does work. Okay, so then next, we have the general form of a second order differential equation, which means I've got the second derivative here, or the second derivative of y with respect to x, plus any function of x, right, will be, we'd be given this in the problem, whatever functions of x they are. It's just the general formula, right? Plus f of x, some function of x times the derivative of y with respect to x, plus some other function of x times y is equal to some function of x, right? So all the y parts, we've got a second derivative part, a first derivative part, no derivatives, and then no y, right? And this is our general form for a second order differential equation. The general solution, right, in most cases, will be in the form, right, and at least all the cases we're going to be dealing with in quantum mechanics, will be in the form y equals c1, some constant c1, can be any constant, times y1 of x plus c2 times y2 of x. What this is saying is that any differential equation, any second order differential equation like this, or almost any, will have two distinct solutions, y1 and y2, right? And they're not like a multiple. It's not like, e to the x and 2 times e to the x, right? Or right, they'll be linearly independent, meaning you can't, neither of them are a constant multiple of another one, right? And so you'll find two and only two distinct solutions. And then if you add them up, right, so say I've got a differential equation that you'll see. Actually, we'll see in our next example, we'll have a differential equation that can be solved by e to the kx and e to the negative kx, right? And so that would mean e to the kx plus 3 e to the negative kx would be a solution. Or 2 e to the kx minus 7i 3 to the it's 7i times e to the kx, right? There just has to be any constant. And so we'll see in these cases of this second order equation, we have this, where the second derivative of y with respect to x is some constant k squared, right? We're just writing it in k squared because it's fairly convenient, right? So usually this would be something kind of easy like 4, right? Like, so that's 2 squared. K would be 2. If d squared y by dx squared equals 4y, we know k is 2. And the solution in that case would be c1 times e to the 2x plus c2 times e to the negative 2x. Notice, right, these two solutions, you can't, e to the negative kx is not a constant multiple of e to the kx, right? These are linearly independent solutions. Right, so again, if we had d squared y by dx squared equals 4y, one of our solutions that we could have might be e to the 2x minus 3e to the negative 2x, right? Or 8e to the 2x plus pi e to the negative 2x, right? Similarly, what if this is not positive k squared, but if it's negative k squared? In that case, the two solutions we have are e to the ikx and e to the negative ikx, right? And again, just arbitrary constants here. Right? And hopefully you can see this, that if you turn k here into negative, if you turn k here into I times k, you'll get, right, when you square it, you'll get that negative sign, right? And so you're just placing it in, right? If you replace everything here, we replace everything on this side with, replace k with ik, you'll get this, right? Hopefully that will make sense. Now, the cool thing here is there's actually a different way to write out this solution. You can write it in terms of exponentials, but you can also write it in terms of sines and cosines, right? Some other constant, they won't be the same, right? But some constant c3 times sine of kx plus c4 times cosine of kx. So for example, if I had d squared y by dx squared equals negative 4y, right? My solutions could be, it could be something like 2e to the 2ix minus 4e to the negative 2ix. But I could also have a solution like 7 sine of 2x plus 9 cosine of 2x, right? Or and note that these constants can be negative, which is why I would be saying like minus something, right? And the reason this works, that you can write it in either way, sorry, I didn't mean to take that out, I meant to take that out, is this. So we know that e to the ikx can be expanded into sines and cosines. Same thing with e to the negative ikx can be expanded into sines and cosines, right? But if you work backwards, right, if you solve for either cosine of kx using these equations or solve for sine of kx, you can find that this also holds true, right? So if you take the general form c1 e to the ikx plus c2 e to the negative ikx and plug in these, you'll see that you can actually write it in as a sum of sines and cosines, as long as you allow C3 and C4 to be imaginary, right, or complex. Same thing here, right? If you allow C1 and C2 to be complex, and you plug in these formula, if you plug in this definition for sine and cosine into this second equation here, you'll get that we'll have some constant times e to the ikx plus some other constant times e to the negative ikx. If you don't believe me that these two are interchangeable, try doing the math by yourself and you'll see that, and then you'll see that you can actually express C3 in terms of C1 and C, in terms of a combination of C1 and C2. You can express C4 in terms of a combination of C1 and C2 as well. And same thing vice versa. You can express C1 in terms of C3 and C4, and you can express C2 in terms of C3 and C4. This will make sense if you actually try to do the math, but if not, or if you've seen it before, you can just trust me on this. Notice one other thing, these are called linear combinations, right? If I'll go back to, take this down, I go back up here. This, right, y is expressed as a linear combination of y1 and y2, which sounds familiar from the vectors video, right? Where linear combination is just some constant times the first thing plus another constant times the second thing, right? So hopefully this makes sense. This is just the basics of the differential equations you will need to know for this course in quantum mechanics. I'll see you in the next video.